So last time we spent quite a lot of time on this example, going through the methods of sketching this. So I just want to go through this problem one more time, and then we've got two more problems to cover today, and then 3 homework problems for you to try. Please do the homework problems. Will be very good practice for the test. Hint, hint. Otherwise, if you need more problems, please see the tutorial. I think there's like 10 problems on this. Okay, but let's go through this one more time. And like I said last time, please have your colors available, right? Here we only needed 2 colors for the 2 parts, but we're going to need quite a few colors for the next couple of problems. So if you don't have colors, sit next to someone that does and share whatever, but it will make learning this a lot easier if you can see the different parts in different colors. Okay, so what we did was we took the function, the polar function, remember this is a polar equation, and we made a little sketch with theta going along here and the radius going along the vertical. Since we're going from 0 to pi, we only drew from 0 to pi. And I made an important note about noting where the function is increasing, where it's decreasing, and the turning points. Right? That helps us with the sketch, which we'll see in a bit. So this first part from 0 to pi over 2, we see that it's increasing. I'm going to call that region 1. So what does that mean? It means the radius starts from 0, and at pi over 2, the radius is 1. It's increasing to 1 from 0 to pi over 2. So from 0 horizontally to pi over 2 vertically, we see that the radius here increases to 1. That's for region 1, we have that in blue. For region 2, we see that it starts at 1 and it decreases to 0. So from pi over 2, you imagine going counterclockwise, pi over 2 to pi, the radius decreases. You see it's getting smaller and smaller, and at pi it is 0. So region 1 and region 2, that makes the circle here. Yeah, and we saw that on Desmos at the end of the lecture. So that was just a quick recap of what we did last time. These problems are going to be a bit more difficult. There won't be just 1 and 2. There will be like 8 parts to it, or 6 parts, but it's the same idea. You draw part 1, you draw part 2, 3, 4, 5, however many parts. It's always the same thing. From 0 to the turning point to 0 for each part. Okay. Any questions on this bit before we get to the other problems? Okay, so this was all from Tuesday. Okay, you should understand that. Let's get on to today's problems. Okay, so here we're going to look at cos 2 theta from 0 to 2 pi. And sine 3 theta from 0 to pi. This one over there, the cos 2 theta, that's about as difficult as it's going to get for tests and exams. Okay, so if you can follow along for that one, you'll be fine for the test and exams. And then here's the homework problems. If you can do these, you got it right for the test already, right? So that will be the homework problems. Again, if you need more help with this, the tutorial has about 10 more problems to go through. But if you can do today's problems and the 3 homework problems, you are fine for the test. Please do not stress about anything more complicated. Okay, any questions on this before we start? Oh, good. Okay, so let's get on with today's work. So sketch the polar curve. Right, so it's the polar curve or function or equation. We know what that is from last time. R equals cos 2 theta on the interval 0 to 2 pi. This is roughly how it's going to be worded in the test and exam. So sketch the polar curve, some function of theta, polar function of theta, with some interval. Okay. It will be roughly 5 marks for that. So it's roughly 2 marks for the side working, figuring out your regions and so on, and then 3 marks depending on how complicated it is to draw the pieces. Just a note on the part marks, if you get some of it right, so let's say the right side, you do get part marks. Okay, I'm not going to give you 0 just because it doesn't look identical. If you do like the right half, but the left half you kind of mess up, I can give you part marks for that. Okay, so don't worry about it being exactly like this. Okay, so first thing we do is draw that little diagram on the side. That will be our side working. So it's going to be cos 2 theta. So between 0 and 2 pi, we need 2 cos graphs. Yeah. So let's do that. So I'm going to draw 1. So that's going to be the 1 cos graph, and then another. Okay, so where I stopped with the first one, that must be pi, because I fit 2 of them in that interval. Okay, so we have one of them between 0 and pi, and another between pi and 2 pi. With that, we can split it up even more to get the smaller angles. That's going to help us out. So this angle, the first one over there, the x-intercept there, remember that should have been pi over 2, but again, we're fitting 2 of them, so that will be pi over 4. All your special angles get halved. So this will be pi over 4. Remember, a normal cos graph goes through pi over 2. This will be pi over 4, again, because of the frequency there. Okay, you can fill in the other angles if you need, but remember, it's always going to be a multiple of pi over 4. Okay, so we have pi over 4, pi over 2, then pi, same thing going through. Next, we're going to split it up into the intervals of increasing, decreasing, like we had before. Now, in the previous case, it was only 2. We had the increasing part and we had the decreasing part. We're going to do exactly the same thing, but here we've got a whole lot more to deal with. Yeah. In fact, there's 8. Yeah. That's fine. So the first part, we know that the cosine is decreasing down to pi over 4. So let's draw this a little bit better here. So we're going to call that 1. Actually, let's start with the colors while we add it here. So that will be 1. Okay, if you don't have 8 colors, try just labeling it with the numbers, but the colors do help. Okay, so that's region 1. Next, from pi over 4, it goes down. So that must be another region. Let's call that region 2. Right, that's where it's going down. Then it's going to go back up again. So that's increasing now. That's going to be region 3. Okay. Then we're back at 0. Then it's increasing again. Let's call that region 4. Then it's going down again. Let's call that 5. Okay. Then we're back at 0, still decreasing. So let's call that 6. Let's pick another color. That one. Right, now we're at the bottom there. Then we're going back up to 0. So that will be 7. Let's pick another color for that. Let's go with this one. And finally, we're back at 0. We're going up to 1. That will be number 8. Let's do gray. So we've cut this up into 8 parts. So when we're doing our sketching, we're going to have 8 bits to sketch. We're just going to do them one after the other, and then that will give us our picture. Exactly the same way as we did number 1 and then number 2. Now it's just going to be 1, 2, 3, all the way to 8. Okay, so let's set up our diagram. Now here, remember these radial lines, 0, pi over 4, pi, and so on going around. Notice here we have pi over 4. Where's pi over 4 in this diagram here? So that horizontal is the diagonal line. Okay, so that's going to be important for us. And then we can put the other one in. Okay. I'm not going to draw the circles just yet. We'll see in a bit what we're going to do there. But let's put in the angles. So we're going to have 0, pi over 4, pi over 2. And it's going to go all the way around. Back to 2 pi. Okay, so how many pizza slices did we chop this up into? Okay, count them. 8. How many pieces did we chop this function up into? 8. Good. Which means each piece is going to be in one of these pizza slices. Exactly the same as what we did here. Here we didn't need these diagonal lines. Okay. It helped with putting in the points, but we don't need them. We could have just done from 0 to pi over 2, and then pi over 2 to pi. 2 pieces, right? Because we chopped it up into 2 pieces. Okay, so the number of pizza slices you chop this up into depends on how many pieces you got here. So in this case, we chopped it up into 8 because there's 8 here. If that frequency was different, you would chop this up differently as well. Maybe it would be 0, pi over 3, and so on. Okay, so just keep that in mind. Okay, but we got 8 here. I don't want to number them because then it gets too messy, but we're going to start off with 1, which we have in green. That's going to be the first bit, and then 2, 3, 4, 5, all the way around 8. Okay, so number 1, what are we doing? We start with radius 1, and we are decreasing the radius until we get to pi over 4, where it's 0. So how are we going to draw that? At angle 0, that's the horizontal, we need to start at 1. So let's choose there to be 1. And at pi over 4, as we're increasing the angle to pi over 4, we need to end up at 0. That's going to be here. Okay. Now, again, we need to imagine 2 things at once. We're going to imagine the angle increasing to pi over 4, and we need to imagine the radius decreasing. And then we'll see what it's going to look like. Okay, so again, we start here. We need to imagine the angle increasing. So it's going to go out like this, but the radius must also decrease. So how's that going to look? So as we increase the angle, I need to go closer to here, right? So let's increase the angle and move to here. Increase the angle and move to here. Does everyone see that? Yes? Okay. So we increase the angle and we need to move to here. So we increase and we need to move to here. Okay. So it's going to be this kind of shape, like that. So let's do that. So first color was green. You use whatever colors you have there. It's going to look like this. I'm going to put the little arrow just to show the direction that we're going to be going through. Okay, so we started here and we ended at the origin. You always need to keep track of where you ended at, because that's when you're going to start for the next bit. Okay, next is blue. We're going to start at 0, the origin, and we see that it's going to -1. So it's going to go from 0 to -1. Now, how do you draw a radius with negative value? Okay. So please put a note here. From theta equals pi over 4 to theta equals pi over 2. That's for this region 2 here. The radius is negative. but you can't draw a negative length. There's something we have to do. Okay, now there's a rule that we need to follow. Okay, it's not too difficult, but you just need to imagine this. So from pi over 4 to pi over 2, that's going to be this part of the pizza slice. Okay? But the radius is negative. So what do we do? Imagine a little position vector, or whatever from physics. From here to some point in here, there's a position vector. But the radius is negative. So what do? We don't draw it in this pizza slice. We flip over 180 and we draw in the opposite pizza slice. Okay, so if the radius is negative in this region, you flip over 180 and you draw in the opposite pizza slice. Okay, so you just need to imagine what's going on here. From pi over 4 to pi over 2, we want to draw here, but the radius is negative. Negative means you flip over 180 degrees. You draw in the opposite. Okay. So this quadrant over here, what would the opposite be? This quadrant here. Make sense? Quadrant 1 goes to quadrant 3 for a 180 flip. Does everyone see that? If I'm up here, what's the opposite? Down here. If I'm over here, where's the opposite pizza slice? Here. Right? You see it's the opposite like that. If I'm over here, where's the opposite? Down here. Okay. So please keep that in mind. When the radius is negative, you do a 180 and you draw in the opposite pizza slice. It's not a quadrant, so I'll call it pizza slice. Okay. You draw in the opposite. So 180 degrees, pizza slice. Right, technically it's called a sector, but don't worry about that. We'll call it pizza slice. Okay, so we need to draw in that little bottom left one. Now, how's that going to work? We see that the radius starts at 0 at the origin. And we need to think of it not decreasing to -1, because forget about the minus now. We've dealt with that. The radius is increasing to 1. The minus sign, we took care of that already, because we're drawing in the opposite slice. So the radius is increasing from 0 to 1. Now, what's that going to look like? What color was that? Light blue. Yeah. So we're going to start at the origin. We're drawing in the bottom left pizza slice there. We start at 0. We end at 1. Angle is still increasing as normal. So let's put in 1 here, which we'll need. So we go back here. So we start here. This part of the pizza slice. The angle is increasing here. Does everyone see that? Start here. Increasing to here. The line will start there and end here, going along the angle. So we're going to start here and curve down. You see that? Okay. You'll see all of them will be something like that. So we start here and end here. Okay. We'll do one more like this, going in full detail. But once we see the picture, we can easily fill in the rest. Okay, but just to get the idea, we'll do one more. And again, I'm putting the little arrow over there. Okay, and now we just continue. Next color is the pink. So we're at the bottom point here, the turning point. The radius is 1. Over here, is radius 1. And we're going up path number 3 to 0 as we increase the angle. Okay, does everyone see that part for number 3? So we start at 1 and we are decreasing the radius to 0, where the 3 is there. Okay, so I'm not going to do the whole thing again. We can see from the picture. So we're going to start at 1. We need to end at 0. How do we do that? Well, the angle increases for that little pizza slice, and the radius must get smaller. Well, it must look like this. Okay, and that's in pink for the third interval there. Okay. And remember here, we were still in the negative. That's why we were doing it in the opposite pizza slice. Because we should have been here, right? From pi over 2, we should have been here, but it's negative, so we drew it here. It just continues as normal. Okay. Let's do number 4. Okay. So number 4 goes from where we just stopped, back at the origin, and it is increasing to 1. So wherever we're drawing it, it should be an arc going out to 1. Where would we draw that? Just from seeing what we've done so far. So we've got sector 1, 2, 3, 4, 5, 6, 7, 8. We need to now draw for that next interval. Which sector will it be in? If you were continuing the pattern. Okay. Hands up if you say sector 1. Well, we've already used that one, so it can't be that one. This one? Hands up. This one? This one? Yeah, good. You're going to use this one. Why? Why this one? Yeah, it's the next angle after this. We did pi over 2 to here. We've done that one already. It's the next one following the angle. And what's it going to look like? We start from 0. We end at 1. So we're starting here. We need to end here. It's going to look like that. Does everyone see that? Okay. That's the last time I'm going to go through that whole thing again. We're just going to fill in the rest now. Yeah, so that color was red. It's going to look like that. Okay. Now we're just going to fill in the rest of the colors. I think you get the idea of how it looks. Okay, next color was this dark blue. So let's do that one. It's going to look like that. I hope everyone sees that. We drew in that pizza slice, so obviously it's going to be in the next one there. And then finally, the last two, it's that pinky color. So let's put that. Okay, I hope everyone sees it should be that one. Okay, the next color is the orangey brown. So let's put that one. I hope everyone sees it should be this. It's just the continuation from where we were. It's never going to jump to some random other sector. It's always continuous. And finally, the gray one, I hope you can see, if we back at the origin and we need to end at 1, it's going to be that. And this is why I said bring lots of colors. You can see each piece now. If you don't have all of the colors, please make sure you number them as we went around. So you can see you do number 1, then number 2, then number 3, all the way to number 8. Okay. This is as difficult as it's going to get for the test and the exams. Okay. If you can draw this one, you can draw any of them. All right. Any questions for this one before we look at the other one? Oh, good. Good. Next one. So it's the same story, sketch the curve. R equals sine 3 theta. where we've got 3 sine graphs from 0 to 2 pi. But here it's only on the interval 0 to pi. So same idea. We're going to do a little bit of side working, find our intervals. So 1, 2, 3, 4, 5, 6, however many we need. Draw in our pizza slices with however many slices we need, and then fill in the little arcs. Okay, so the little side working we need is sine 3 theta from 0 to pi. So we're going to have 1 full sine graph and a bit because of the 3. So we're going to have 1 full graph. That takes care of the 1 and a bit. So that will be from 0 to pi. Okay, so let's fill in some angles. So if the whole thing there is pi, we can fill in the crossing points and the turning points. So the first one, that will be at pi over 6. Right, because it was pi over 2, but then we divide by 3, so pi over 6. And then this crossing point here, that will be at pi over 3. Then we got 2 pi over 3. You can fill in the other angles if you need. Now we're going to chop this up into the parts where it's increasing and decreasing. So the first part, from 0 to pi over 6, it's increasing. So let's call that number 1. I'm not going to try use the same colors. I'll just use different ones for this one. So that will be number 1. Then from pi over 6 to pi over 3, it's decreasing. So that's a new number now. Let's call that 2. From pi over 3, we're decreasing. That's a new number. Let's call that 3 over there. Now we're at the bottom, going back up. Let's call that number 4. Then we're going up to the top last turning point there. That will be number 5. And finally, coming back down to pi, let's call that number 6. So why are there 6? Well, the period there was 3. If each little bump there has 2, there's going to be 6 pieces. Right? Because if you go up, you must come back down. So 3 bumps, 2 intervals per bump, that gives us 6 parts to draw. So let's draw this. Now here it's going to be a little bit different because this turning point over here is at pi over 6. Previously we had it at pi over 4. So it's a little bit different now. It's going to be something like that. But this angle now is pi over 6, not pi over 4. So you need to be careful how you draw these lines. Okay, it doesn't need to be exact, right? But as long as you keep track of where you are, it should be fine. Okay, and then we're stopping there at pi. All right, so let's sketch this. So number 1, we see from 0 to pi over 6, it's going to increase to 1. We start at 0, we want to end at 1, it needs to increase, so it can only look like this. Because we start at 0, we end at 1, that's the only way to do that. Okay, so that's in gray. Again, I'm not going to go through the full details, we know what it should look like from before. Then the orangey color, number 2, from pi over 6 to pi over 3, that's going to be somewhere in between those two. It must go from 1 down to 0. And then we can do the third one. So it must look something like that. Okay, now number 3, we see it's negative from pi over 3. It's negative. So we should be drawing it in this bit over here, right? From the pi over 3 bit. It should be somewhere over here, 60 degrees. But it's negative, so we flip over and we draw it in the bottom bit there. Okay, that color was pink. Because that was the pi over 3 to pi over 2. Okay, so it should have been in this top portion here, around the 60 degree area, but it's negative, so we flip over and we need to draw it here. Okay, next, number 4. It's still negative, so we still draw it in that bottom bit, but now it goes from 1 to 0. That was in red. Yeah, and now we've made a full loop. Now we're back over here. Okay, finally, number 5. We're going to go from 2 pi over 3, so that's going to be where we just were, from 0 up to 1. Right, and it's somewhere between 2 pi over 3 and pi. So it's going to be in that top left bit over there. So it's going to look like this in the dark blue. Okay. Right, for this section, where's this angle? Over here. Pi is over here. So where's that 2 pi over 3? Check your angles. Okay, we're in this region here. So from 2 pi over 3 to pi, okay, we're in that region there. So where would that be here? Split this. You see that? 2 pi over 3 down to pi. You see that? Okay. And then the last bit, from where we were, so along that line there, that's where we just ended, over here, and then down to pi, that will be the last bit. That was in green. Okay. So from 2 pi over 3 to pi, that's that last little bit there. Okay, if the radians is confusing you, you can convert back to degrees. So if it's easier to see where 60 degrees is, that's fine. You can work in degrees. I just want to see the final picture. Yeah. So if you want to put 0, 90, 180, that's fine, right? I just want to see the shape. Okay. So we get something like this. Any questions for this one? Oh, good. Okay. All of them are exactly the same. You just take this, you chop it up into the intervals, and then you draw each one. Okay. It's all the same, same working. Any questions before we move on? Oh, good. Okay, again, please do the homework problems. They will help you for the test. Okay, I will leave it at that, right? Very helpful for the test. Okay, next bit, vectors in polar coordinates. So you're familiar with the usual Cartesian vectors. You've covered that a lot in physics. So what we're going to do now is convert all of the stuff you did in physics with Cartesian coordinates, we're going to convert it over to polar coordinates. So just a quick recap on vectors, unit vectors, and so on. We're going to do that in Cartesian. You should know all of that already. And then we're going to convert it over to polar coordinates. So in Cartesian coordinates, we have the following. We have x and y. Any point in this Cartesian plane xy, we can draw a vector going to that point. And we can decompose that vector into an x part with the I hat unit vector in that direction and a y part, which is something in the j hat direction. Okay, so over here, we can have our unit vectors I hat and j hat. So any vector here, we can write as something I hat, something j hat. I'm going to put the little arrow at the top. That's just my notation for the vector. Okay, and we have the little, you use I hats and j hat, right? Okay, sometimes there's x hats and y hats. Let's just stick with I and j. Okay, so we have this vector. We can decompose it like this. Now, the interesting thing with Cartesian coordinates that polar coordinates does not have is that this little I hat, j hat frame is the same everywhere in the Cartesian plane. So a lot of the times you don't even think about it, but if you draw a vector over here, like this, there is also a little I hat, j hat frame here. Yeah, and it's the same wherever you are, so a lot of the time you don't even think about it. But at each point, there's a little vector I hat in the x direction, and a little vector j hat in the y direction at every point. Yeah, but it's the same everywhere. In polar coordinates, this is not the case, and it's going to cause us some issues. So let's draw in our polar coordinates system. So we got something like that. We know that these radial lines go out at angle theta, and we have these circles that go out with radius r. Any point in this polar plane will then be given by r and theta. Now we're going to draw the same sort of vector like we had here, but we're not going to decompose it into the I hat direction and the j hat direction. In polar coordinates, we're going to have the r hat direction and the theta hat direction. Okay, so let's pick a point. Let's say this one over here. We're going to have an r hat, which is a unit vector in the radial direction. So it's going to look something like this. And we have a theta hat that points into the angular direction. What do we mean by angular direction? It points in the direction of increasing theta. In this case, increasing theta means counterclockwise. So we have a unit vector going in the counterclockwise direction. We call that theta hat. And they are perpendicular to each other in the same way that I hat and j hat are perpendicular to each other. Okay. Everyone clear on that? Okay. At any point, you can draw r hat going in the radial direction and theta hat in the angular direction. But unlike Cartesian coordinates, where this I hat and j hat are the same everywhere, this r hat and theta hat will change everywhere. So let's pick another point to see that. Let's pick this point over here. Now r hat needs to go in the radial direction. So it's going to go left. And theta hat, that needs to point in the angular direction. That's going to point down, because that's the direction where theta increases. And we see they're still perpendicular to each other. Notice that at different points, r hat and theta hat are different. In that top right point, r hat goes out, top right, theta hat goes left. Okay? At this point, r hat is now going left, and theta hat is now going down. This little basis frame here, do you guys call it that in physics? The frame of reference? Anyway, the vector frame there changes from point to point. So, very big exclamation mark. Unlike in Cartesian coordinates, r hat and theta hat change from point to point. Yeah, and that's going to cause us some issues in a moment. Okay, is everyone clear on this diagram? So you pick a point, you can draw r hat, you can draw theta hat. You pick another point, you can draw r hat, you can draw theta hat, and it will be different wherever you are. Okay. Any questions on that before we move on? Okay. Okay, so the main thing for today, so we're going to do this as a physics application. We're going to find the position vector, the velocity vector, and the acceleration vector in polar coordinates. Right, you know what they look like in Cartesian. We're going to now convert. Okay, we would like to convert the position vector, r with the little vector thing at the top, the velocity vector, and the acceleration vector. You can do the same with any vectors, but we'll just do it for these three. From Cartesian coordinates, right, x and y, into polar coordinates, r and theta. Yeah. And once you know how to do it for these three, you can convert any vector from Cartesian to polar. Yeah, depending on whatever physics problem you're trying to solve. So let's start off with the position vector. We're going to write it in Cartesian form. We're going to use the transformation laws that we looked at last time and convert it into polar form. So the position vector in Cartesian, we know that is x times I hat plus y times j hat. Right? You've seen that many, many times. So this is in Cartesian form. How do we know? Well, we have x and y, we have I hat, j hat. This is in Cartesian form. Right, because we've got x's and y's, and we've got I hat and j hat. That's Cartesian. We don't want that. We want to write this as r and theta with r hat and theta hat. So how do we do that? We have an x. How do we convert x to polar coordinates? R cos theta. We have a y. How do we convert that to polar coordinates? R sin theta. Now we have this common factor of the radius. We can take it out. Now this vector in the square brackets there, that is r hat. Okay. So we'll see a little example on that. But this is r hat. How can we see that? Let's put in angle 0. What do we get? If the angle is 0, what is left? What's the vector that we get? I hat. So angle 0 is in the I hat direction, in the x direction. That makes sense. Let's put pi over 2. Pi over 2 gets us j hat. That goes up, right? So at pi over 2, the vector is j hat in the vertical direction. Well, that makes sense. That's what we want. So angle 0, it points horizontally. Angle pi over 2, it points vertically. What about at pi? Put pi here. What do we get? We get minus I hat. Where's minus I hat? Well, that's going to the left. But that's where pi is. Okay. Does everyone see that? Okay. So this is our definition for r hat. Over there. Okay. So that is our position vector in polar coordinates. So the position vector r in polar coordinates is just r times r hat. Very, very simple. It's whatever the length is in the radial direction. You should have seen this before in physics. Yes? No? Not yet. Okay, you will. Now let's look at the velocity vector. The velocity vector is the derivative of the position vector. Okay. So we know what the position vector is. Let's find its derivative. So it's going to be d by dt of r times r hat. Now, when we do derivatives in Cartesian coordinates, we did d by dt of x and d by dt of y. We didn't worry about I hat and j hat because those were constants. But what did we say over here? R hat and theta hat change from point to point. They are not constant. So when we are doing the time derivative, both of these depend on time. In Cartesian coordinates, the I hat and the j hat do not depend on time. Here they do. The r hat and theta hat does depend on time, so we need the product rule. Okay, these unit vectors are not constant. Okay, these unit vectors are not constant. So whenever you have a product with a unit vector, we need to do the product rule. So this is going to be d by dt of the first factor. I'm going to call that r dot. You've seen that before? The dot for time derivative? Yes? No? You have? Okay. So it's the derivative of the first one. We leave the second one alone. Plus product rule. We leave the first one alone and then do the derivative of the second. Yeah. Now, how do we do the derivative of r hat? Well, we know what r hat is. We defined it over here. So let's substitute and then do the derivative. So it's going to be d by dt and what we had before. So the derivative's going to jump inside. Now we need the chain rule because the theta depends on time. The angle can change. So that theta there is not just theta by itself, it's theta of t. So theta can change. So it's cos of theta of t. Yeah. Make sense? So let's do the derivative. Because it's cos of theta of t, we need the chain rule. So the derivative of cos, negative sign, and then by the chain rule, we multiply by the derivative of theta. So this is going to be r dot r hat plus r minus sine theta theta dot plus cos theta theta dot j hat. We've got theta dot common to both of those, so we're going to take it out. So this is going to be r dot r hat plus r theta dot, and then whatever's left after taking out the theta dot. Okay. Now we're left with that stuff in brackets. We need to figure that out. So we're going to do a little bit of side working here. Okay. I'm going to claim that that stuff in brackets there is actually theta hat. So how do we see that? So let's go back to the diagram. We had r hat doing something like that, and theta hat was always perpendicular. Right? It's always perpendicular to r hat. So let's write down what r hat was. Okay. And we see that theta hat over there is always 90 degrees ahead of r hat. You've got r hat, you rotate by 90 degrees, that will give you theta hat. Does everyone see that? Okay. So let's take r hat and increase the angle by 90. So theta hat will be cos of theta plus 90, and sine of theta plus 90. Okay, because we have r hat, we rotate by 90, that must give us theta hat. Okay, cos of theta plus pi over 2, what's that? Special angles, negative sign, thank you. Okay, and then sine of theta plus pi over 2. Cos, yeah, co-functions, right? They're 90 degrees apart. Yeah, so that's our theta hat, which we see is exactly the same as that square brackets there. Right? That bottom bit, that's the same as the square brackets. So we're going to substitute in our theta hat. And so we get V is equal to R dot R hat plus R theta dot theta hat. Okay. Now in physics, we give these two special names. The velocity in the radial direction, we call that the radial velocity. And the one in the theta direction, we call that the angular velocity. It's an angular direction. Yeah, the second term, you might see it written differently. You've seen that before. If omega is the angular velocity, you multiply by the radius, that gives you the tangential velocity, right? Yeah, that's exactly what we have here. R theta dot. Theta dot is the rate of change of the angle. It's the omega, angular velocity. So radius times that will give us the tangential velocity. And if we draw a picture, we can see this quite clearly. So let's say we have a particle going around in a circle, like that. In polar coordinates, how would we describe where that particle is? So here, we've got the position vector going to the particle. Now, at that point, we can draw r hat. That's going to go outwards. So the velocity in the radial direction is r dot r hat. That's going outwards. And what about this one? R theta dot theta hat. That must be at right angles. But what is at right angles to a circle? The circle's radius. What do we call that? The tangent. Okay. So here we've got r dot, the radial velocity in the radial direction. And we've got r theta dot, the angular velocity in the tangent direction, going around. Okay, so any vector v, we can decompose into the radial part going outwards and the tangential part going in the angular direction. Okay, you would have seen this picture many times in physics, right? Orbital motion. Okay, and then the last thing for today, the acceleration. So the velocity is the time derivative of position. So the acceleration, that's the time derivative of the velocity. So it's the time derivative of what we just calculated. So this is going to be d by dt of the radial velocity and the angular velocity. So we need to calculate this now. So the first term, it's a product. Remember, r hat is changing. It's not constant. So we've got a product. We need the product rule. So this is going to be the derivative of the first one. So r double dot, r hat plus r dot, and then the time derivative of the second term. Plus, and now we've got d by dt of a product of three things. So we need to do the product rule for each one. So let's do the derivative of the first term. Leave the others alone. Then the first one we leave alone. Derivative of the second. Now the first two we leave alone, and we do the derivative of the third. Yeah. So we end up with these terms here. Any questions before we get to the expansion and derivatives? So everyone's following. Right. So let's substitute for r hat and theta hat, and then we can do the derivatives. So this is going to be r double dot, r hat, plus r dot, d by dt of r hat. We know what that is from before. Plus, then the next two terms, we just leave as is. They're already done. And the last one, we need to substitute so we can calculate that last derivative. And then the theta hat, we calculated that just before. And that was all of them. So we've got these two derivatives to do. Then we're just going to collect some like terms, and then we'll be done. So this is going to be r double dot r hat plus r dot. Okay. Now again, it's cos of theta of t, so chain rule. So it's going to be minus sine theta, theta dot. Plus sine of theta of t, so it will be cos theta, theta dot. Okay, these other two, we're just going to keep. Okay, plus r theta dot. Same thing. So it's sine of theta of t, so we need to do the chain rule. That will be minus cos theta, theta dot. Okay, and then the last one there, cos of theta of t, that will be minus sine theta, theta dot. Sorry, j hats. Okay. So we've got this mess over here. The first bracket and the second bracket, they both have that theta dot there. We can take that out. And then what's left over, we'll see that's going to be theta hat and r hat after the factoring. So here and here, we can factor that out. And here, we can factor that out as well. Okay, so that's going to be r dot theta dot. And what's left over? Minus sine theta and the plus cos theta. Yeah. Then the other two, we're not doing anything with that yet. Okay. And finally, here we can take out a minus theta dot. So it's going to make the plus into a minus. Okay. And we're left with cos and sine. Okay, so the first square bracket, we recognize that. That's theta hat. And the second square bracket, we recognize that one. That's r hat. So finally, we can combine all the like terms together. So everything with r hat, we're going to put together, and everything with theta hat, we're going to put together. So we have r double dot, r hat, and the other r hat term is at the bottom there with the blue. Plus, and then let's put the theta terms together. So we're going to have r dot theta hat. R dot theta hat. We've got two of those there in that first line. And then we've got r theta double dot again on that first line. And we've done. So we've got the acceleration in polar form. Now we've got four terms here. and 4 chances for some bonus marks. Okay, so we're going to name them. First term, what is the physics name for that? Yeah? You don't know, okay? Sorry? The whole thing's acceleration. What do we call that first term? It's 3 marks for each. So 30% in the next quiz for each one you get. Yeah, it's the last bit of bonus marks because we got the test coming up. So remember, the next lecture is only going to be on the Thursday. So last chance for some bonus marks. Okay, 5, 4, 3. Sorry? Was that? Oh. Where was that? 2, 1. Okay, no one got the first one. It's the radial acceleration. It's the radial. Double dots is acceleration. R is the radius. It is the radial acceleration. That was the easiest one, so that's gone. Okay. Next one. What do we call that? Nope. That whole thing, that second term. What do we call that in physics? Yeah? Very good. Okay, you get your 30%. Centripetal. If you replace the beta dot with omega, you get minus r omega squared. Yeah, I'm going to have a word with Mr. Evans. Something's minus r omega squared, right? And remember what we said earlier here. V is r omega. So omega is V over r. You've seen that before? The centripetal acceleration, centripetal force. I heard someone say R, so I think you've realized. You might have seen this one. Yeah. You're going around in a circle, it's the force going inside. Okay, next one. Yeah. Yeah, I'll give you that. Sure. Yeah, the angular acceleration. But yeah, transverse if you want to think in terms of that. Right, you got the one parallel to where you're going, and then transverse, that's the other way. So technically correct, that's fine with me. Extra 30% in the scripts. And finally, the last one, 2r dot theta dots. That will be 40%. Because I just made it up now, so 40%. Right. The other ones were 30, this one's 40. You might not get it, but if you do, it's worth more than the other ones. Think back, Mr. Evans' class. What did he teach you? Yeah, let's make it 50%, and I need to go soon. So, extra 50% in the quiz, because I can. Come on. Yeah. Coriolis, well done. It's the Coriolis. Okay. Okay. So please make notes of the names. You will see that later in physics. You should have seen it with orbital motion, but next year, definitely in mechanics, you will cover those. Okay. So later on, it's a bit more advanced than this. So you don't do plain polar coordinates. You'll do polar coordinates in 3D. And then there's a lot of stuff you do with pendulums rotating and all things like that. You'll see that next year. Okay, so those doing mechanical engineering, you'll see a whole lot of this come up later. Okay, with pendulums rotating around the Earth and things like that, you need to understand how to go from polar to Cartesian and Cartesian to polar. Okay, very, very important for anything rotating in mechanics. All right. So that will be it for the class test 3. Okay. So it's everything up to and including this, not the names. Don't worry about that. So that will be for class test 3. Remember, Monday is a holiday. Okay. Because the Sunday is the Women's Day. Then we get the Monday off. Okay. We don't have lectures, but you have the day off. Tuesday is the test. Thursday, we start with the new work for class test 4. Okay. Please remember these tests are very close together. Okay. It's about 3-4 weeks apart from each other. Okay. So not a lot left. Okay. Any questions for the test? You're all good. Okay. So differential equations up to and including this vector stuff for the test.